Welcome, folks, to the session about semi-structured models, queries in the big data era, and particularly the SQL++ of the Couchbase Analytics that you must have already heard about. There is a bit of echo, right?
It's not just a video.
Okay.
You're on video. So.
Oh, I am on video. Okay, fine. So this is a work that had started at UCSD, where I am a professor, when a bunch of us looked into the multiple query languages and models for semi-structured data out there. Then we said, okay, let's actually design something that is capturing sufficiently all the functionalities we have seen out there and make it as SQL compatible as possible. And that's where we talked extensively with the UCI team of UC Irvine team of Professor Mike Carey, and then with Couchbase Analytics. And after many rounds of back and forth and a lot of feedback, there is a language that came up. And on this, how this language came around, it's something that goes on much more than the last few years of effort of these people. It's really something that is building up on many years of database research and development on query languages that we're going to see soon. So here's the first piece of news. Mike Carey made this clear yesterday as well at his talk, that semi-structured data have arrived. By semi-structured data, we mean data that have nesting, data that may not have schema, data that may have only partial schema, data that are not homogeneous. And they are in multiple forms. They are in JSON, in NoSQL databases. They are in logs. They are in columns of relational databases. And here we will mostly care about the JSON form of semi-structured data, and to be more precise, a somewhat enriched form of semi-structured JSON data as the one that you see now on the slide, which we will talk about further as we proceed, where the enrichment is that you may also have some rich types as opposed to just Boolean strings and integers. Okay. Now, as we said, this is not the semi-structured data in JSON and what comes next in queried languages is not necessarily new. It has many close relatives in the past. There was XML. Before XML was the object-oriented data model. Before that was the nested relational data model. And of course, it has many relatives now, like Google's buffer protocols and Parquet and so on. A lot of the stuff that we will be talking about actually can carry in principle over to Google's buffer protocols or Parquet and so on. Okay. And when you have so much semi-structured data out there, something obvious, an obvious need emerges that you need a query language to actually query them, right? And when we say query language to query them, what do you want? Well, you want something like SQL, but for semi-structured data. Okay. And as Couchbase said a few years ago, what you truly need is something that is declarative. That's a healthy feature of SQL. It has a lot of expressive power on what analytics you can do, yet at the same time, is not working only on the flat tables as the SQL that Don Chamberlain here invented many decades ago, but also works on semi-structured data, works on JSON data. Okay, and the need was so obvious for semi-structured query languages that right now there is a lot of them out there, right? And something as simple as the SQL query snippet that you see on the top left corner there is doable in many query languages. It's doable in MongoDB, in Jackal, of course, in Couchbase Analytics, in JSONic, in Pig, and in all of them with another slightly different, frustrating language, right? And Going back to the history that Mike Curry presented yesterday, why did the previous efforts on semi-structured data didn't stick? Well, one reason was that there was a lot of dialects that do the same thing, but they're not the same. And there was often significant distance. That was definitely the case in XML and XQuery from SQL. Okay, so that's a problem. I mean, a better language was needed. And there is a second problem with all of that stuff that you would find out there from MongoDB and many other vendors, which is that very often, instead of finding a formal semantics for the language, what do you get? Instead of formal semantics, you get Stack Overflow, right? When you don't know what the semantics mean or how to do something, you go to Stack Overflow, right? And you hope that someone else knows. That's not good for a query language. Now, a third problem that people face in this space is a bit historical, and actually Couchbase, and there was Couchbase before Couchbase Analytics, is actually faced the same problem, which is that these systems originally came out of key value stores, where effectively the query language was pretty much give me the key and I will give you the value. So rich. And then some of them, if you talk about some other ones that are more of the NewSQL or JSON, you may think of them as SQL with special UDFs. But really, none of them was a systematic effort of how am I going to capture the expressive power of SQL, or why limit yourself on SQL when you go semi-structured data and don't say how am I going to capture the expressive power of XQuery, right? So they didn't go like that, right? That leaves a lot of the efforts out there with a lot of limited query capabilities. Now, keep in mind here that this problem, along with the problem that everyone speaks a slightly different language, which is not looking like SQL, creates a really explosive situation that makes it hard to understand what each one is and is not doing. So in light of this, the first thing that we had done, and that started at UCSD some years ago, we said, OK, let's look at all these query languages out there to see what is their fundamental differences. After you take all the funny syntax out, what is fundamentally different, right? And how we can bundle all of these abilities into a single language. And that's how SQL++ came up. And it was not just a single language when we did it. It was rather something like a configurable language that you could, it was giving you a lot of options for things. And the idea here is to have a data model and a query language for querying structured data as well as semi-structured data. And we want to have here full-fledged expressive power. That is, do the things that you do in SQL at the very least, but on semi-structured data. Definitely a language that has clear declarative semantics, in the sense that SQL has declarative semantics. You specify what the query should be doing. You don't specify what is the computation that does what is to be done. And the third thing is to be as aggressive, as backwards compatible with SQL as possible. Okay. And the good news is that this can be done. That is, I hope that I will convince you that what is now SQL++ and what Couchbase Analytics offers is really based on a minimal adjustment of the SQL semantics, really the SQL tuple calculus, to account for semi-structured data. Okay, so the message I hope you will take is that with limited extensions and mostly restriction removals from SQL, you can actually query JSON data, you can query semi-structured data. Okay, so let's go here. So we said we want SQL compatibility, but also you want to capture semi-structured data. So let's go step one into the data model. How should the data model look? And we got here the SQL++ data model, that you may also think of it as a JSON++ data model. You may think of it as a superset of both SQL and JSON at the same time. If you are of the SQL persuasion, then you may think that what is happening is that you are extending SQL with number one arrays. That is, if you had an SQL database, every attribute of a tuple would be a scalar. Well, here it is an array that has its own tuples. Number two, these tuples may be heterogeneous. For example, look at the tuples within readings. One of them has nitrogen oxide, the other one has carbon monoxide. So they don't have to have the same schema as SQL tuples would do. Number three, actually anything, any arbitrary composition of arrays, bags, and tuples could be a legitimate data set, a source of a query, or a source of a subquery. And we do mean this. For example, here is something that looks very much unlike SQL. This could be one legitimate data source for an SQL++ query. This source is an array, and its elements are arrays, and mostly they have numbers, but sometimes they have numbers and tuples. And all of this is fine because, as we said, any combination goes. Now, you may think also that there is an extension here of JSON. And probably the most important one, I'll skip the one about bugs, the most important one is that, JSON comes with very few types, string, number, Boolean. You really need an enriched type system. So here, for example, you have got the time having values of type timestamp. Okay. So, and we denote with a timestamp constructor that it is a timestamp there. So you see that you can basically say, I got an umbrella over both SQL and JSON to get there. Now, what happened to schema? Because when we do SQL databases, the number one thing that we start with is designing a schema, right? And Couchbase came along a few years ago and said, no, you can go more flexibly than that. You can just throw your data in some store. So what happened to the schema? So here, the approach that we say is that the semantics of the query language, so first of all, you can have data that have no schema, and the semantics of the query language that is coming next do not depend on the presence of a schema. Okay, that's very important. That doesn't say that you will always have to stick without a schema. You could imagine versions that do have a schema or have a partial schema. So for example, this is something very much alike to what the UCI's and Apache *DB is doing, that basically says, here is my partial schema for some data. Okay. Any question, folks, so far when it comes to the data model? So think of it as an umbrella over both SQL and JSON. Okay, so now let's go to the language. So remember, we said that we want to go from SQL to SQL++. So what does this mean? Well, we want our queries to exhibit a lot of the abilities that XQuery and NoQL were exhibiting, but being very compatible with SQL 92. And why SQL-backwards-compatible? Well, because for starters, that's what we teach, right? And that's what most people out there know. But also because, and a separate goal that we had, is that there is a very extensive literature on how to build an SQL query processor. It's really good to build up on this literature. Okay, so let me define here what I mean by backwards compatibility with SQL. So what I mean here by backwards compatibility with SQL is the following. Consider the piece of data that you see here. Okay, Think of it like the JSON array. Its purpose is simply to signify that I don't care about the order of this, like being the top level collection, and you don't really care about the order. And you got here, on this particular collection, you got some tuples, and notice that these tuples are pretty well behaved. All of them have the same attributes, right? So it's like SQL tuples, very homogeneous. So you could think of this as well as being this table that you have here, okay? And then consider some analytics that you would like to do on this data. You would want to say find sensors that recorded a temperature below 50. That's one legitimate analytic that you may want to do. It is expressible with the SQL query that you see, the one that says select distinct from readings, the ones that are below 150. And this query runs on tables, but basically what we mean by SQL compatibility is that as is, it should run on this JSON data as well. Okay, so number one property here is that we want every query that is, we want as much as possible of the functionalities that can be expressed in SQL to be expressible also in SQL++. A second property, we want to the maximum possible degree every SQL string that has a meaning in SQL to have the same meaning in SQL++. Okay. And now, okay, fine, we said that that's the compatibility. How do you go then to the extra abilities? Well, the extra ability is queries that input and output any JSON type. And we'll have to adjust here the SQL syntax and semantics for basically having heterogeneity and having complex input and output values. And the good thing, I hope I will convince you on this, is that this can be done in a very minimalistic way. Okay, so here is the minimalistic example that says how you can basically carry over your SQL knowledge into querying JSON data with SQL++. So now, on purpose here, I have put a source of data. I'm calling it readings. Okay, so you have some source that is called readings. And on purpose, this source doesn't look like what SQL would look like, right? So it is an array of numbers. That is your source. It is not an array of objects, right? It's quite far from what you would have in SQL. Okay, but it is one legitimate data source. On purpose, I have here an example that really creates some distance from SQL. And now you want to do a query that says find the highest two sensor readings that are below 1.0 and output them in tuples that have an attribute carbon monoxide and such value. Okay, and if you stare at the data, this is the result that you should be getting. Now, here is the query that is doing this. As any query should be written, let's actually, instead of going select from where, let's go from where select, which makes it easier to understand what is going on. So this language, SQL++, is a functional language where effectively every clause, the from, the where, the order by, the limit, the group by, the select, all of them operate as functions that input and output bindings for the variables. What do we mean by this? Let's go to our example. Notice the from readings as R is supposed to have the variable R range over the collection readings. So imagine that what comes out of it is a bug. Again, the symbol here is to signify that it is a bug as opposed to an array, or basically an array that you don't care about the order in which you put the data inside. And notice that this bug has got tuples in them. These are really tuples. Now you may say, well, if it is tuples, why you didn't use the usual JSON tuple symbol and you used the brackets? Well, I used it simply to signify that all of these tuples that you have got here are homogeneous. All of them have the same structure. Variable takes this value. Okay, and notice what is the values. The values say that the R variable is ranging every time over another value of the input collection. That's how you should be understanding the from. Okay, not unlike how you should be understanding the from in an SQL query, right? The bindings of the variables that appear in the from clause. And then comes the where clause and does its usual thing, which is it keeps only the bindings that are less than 1.0, and then comes the order by and does its usual thing, that is it takes a bug, that is a collection that the order was not specified, and produces an array, a collection where the order is specified. And then comes the limit and keeps the top two, and then comes the select and is really constructing an output out of these bindings. So what is the lesson here? The lesson here is that really the query can be understood as variable bindings, bindings of the variables of the from clause, flowing from clause to clause. Not unlike SQL at all. That's how we would explain SQL as well. Okay, let's skip the next example and go to this example. This example, forget the gamma as well, and just look here. It says now my readings was a top-level collection that had the number 0.3, a tuple, null, and C. It's an heterogeneous thing, right? It's not all numbers anymore. And again, I can have a query there, a query that says from readings as R, the R, notice what's happening to the R now. Each one of the R's, each one of the instances of the R binds to another type. And that's perfectly fine because this language doesn't need schema, doesn't require homogeneity. Couchbase Analytics doesn't need schema, doesn't require homogeneity out of the data. Okay, now here comes the second important piece on that is going to show you that a lot of expressive power can be obtained without going a big distance away from SQL. You can have correlated queries everywhere, and actually the mere mention of a variable, an expression, you can think of it as a query itself. So notice, folks, what is this example says now. This example says that my source now is called sensors, okay? And it is an array of arrays. Okay, and in this array of arrays, I still have the same problem. I want to say find the highest two sensor readings that are below 1.0. Except that now I will have to range over all rows and then on each row go to each one of the numbers here. Okay, how is this done? Well, I'm having two variables in the same way that you would have two variables in a from clause of an SQL query, two variables ranging over two separate tables, except that here there is a correlation between the first item of the from clause and the second one. So you should basically be thinking here that the S variable is ranging over the lines, and then the R variable is ranging over the items of the S. So in terms of the bindings interpretation that we discussed before, here is what you would be getting out of this example. If you stare at it a bit, you will see that what's happening is that the S and the R are basically doing all combinations of a row with one element in this row. Okay, stare at it for a while and it becomes quite obvious what's going on. Again, folks, notice, not far away from SQL in the sense that the from clause just delivers bindings of the variables that appear in the from clause. The special feature here is that the second variable was actually dependent on the first variable. Okay. The rest comes as usual. The where clause is qualifying, the ones that are less than 1.0, the order by is ordering, the limit is keeping the top two, and the select is building it up. Okay, so the language is functional. And a good thing about functional languages is the high composability. Essentially, you should be thinking here that variables generate environments within which the subqueries operate. So you can have subqueries within subqueries within subqueries to any level. And it can look pretty elegant because when you're looking at a subquery, the subquery is making sense regardless of whether the environment came from outer variables or outer names in there. So composability has been a very good idea in past query languages like OQL and XQuery. It's definitely worth keeping this legacy. It is easy to create nested results out of the data that you have got. So for example, here we see a situation that we have got a sensors data set and a log data set. The sensor is listing a bunch of sensors. The log is saying sensor 1 had reported that carbon monoxide at this time. And then I want an output that is basically grouping the readings by sensor. Okay, how difficult it is to do this? Well, not difficult at all, because all that you have got to do is have a from clause where the S is ranging over the sensors, and then notice what's happening in the select clause. I basically have got a nested query in here, and what this nested query is doing is for every sensor that's coming out of the from clause, for every sensor, it's evaluating on the logs the query that says, hey, find for me all the log entries that pertain to this sensor, right? And all of them are going to become a result, a collection that's going to become the readings. That I'm going to name it readings. Notice how naturally the whole thing came. All that you needed to do is to basically have a nested query that is using variables from its encompassing query, as you would do in SQL, with the caveat at this case that I didn't bother to say that, well, an SQL query that appears in the select clause better evaluate to a scalar. It was perfectly fine to say it evaluates to something, and this something is the result of readings. It is the new value of readings. Okay. And here is that we will put the slides online. Here is how you can understand again this semantics by basically visualizing bindings that come out of the from clause, and for each one of them you activate the nested subquery. And here you got a particular example where this is just the nested subquery and is evaluated into an environment that has the data, but also the bindings that come from the outer clause. This is an example of the goodness of the composability. Okay. There is a bunch of issues that I would like to quickly go over. One issue that we may have to deal with when order comes in the mix. Notice that in SQL, the input data do not have an order. They are a bug, right? So SQL allows you to create order for the output by using the order by, but SQL doesn't tell us anything about how to understand the order of the input data. So something has to be done there, because when we have a JSON array, we may want to actually make use of the order in which we find items. And some languages in the past, like XQuery, had attempted to deal with it, but they went into an approach that said, well, let's deal with order by simply trying to preserve in the output the order that we had in the input. That thing sometimes is not enough, and perhaps it's creating undue complications in the implementation as well. So here, we say something else. So here, there is a little extension over SQL. The example is the same that we had before. Find the highest two sensor readings that are below 1.0, but I have added something extra on the output, the coordinates. So think that every piece of data here has an X and a Y coordinate. So this is the X coordinate, this is the Y coordinate. So when I find here a sensor reading that is below 1.0, for example, the 0.9, I want to say that the 0.9 has coordinates 3 and 2, right? 3 and 2. 3 on the x and 2 on the y. And this is done by making a bit of an extension to the from clause by saying the s is ranging over the sensors, but as it is ranging, I also want another variable y that is picking the ordinal number of the particular element, right? So here you're going to get, this is going to be the first s, and the variable y is going to be 1, because it's tagged to the first one. Okay, and keep going like that. And then do the same with the XDR. If you have got this power, then you can do order preservation simply by adding back the order by. So notice here I'm going over the data. I'm picking the y and x coordinates. And if I want to say, hey, I want to output the data in the same order that I found them, that really means output them by y ascending and x ascending. It's a question, and I don't think that anybody or the Couchbase Analytics team has resolved it definitely of whether we want to do something like the X query preservation, order preservation semantics, where you would say, well, I don't want to write this exercise with the X's and the Y's to get the job done. I just want to preserve the input order. And so there is a bunch of things that we are talking, and motion will be happening in the next months on such issues. Let me get actually to the summary. There is a lot of features here. There is features about iterating over attribute value pairs that I'm going to skip. Constructing, pivoting and unpivoting out of tuples. I'm going to skip this. The slides will be online. There is a version of correlating clauses in the from clause that looks like outer join, as opposed to the one that we saw that looks like correlated join. Again, I'm going to skip over this and leave it to the slides that you may want to check online to tell the job. I should say how well have we done on our original goal, SQL compatibility? Very well. We have done very well. There is very few points that is actually SQL is causing a little bit of attention, and we may be looking more. One of them is SQL's implicit coercion of nested queries in where and select into scalars. Another bit of a tricky one is the fact that SQL, what exactly are SQL tuples? In half of the semantics of SQL, they appear to really be tuples in the sense of attribute value pairs, but in some corners of the semantics, they are really fixed arity arrays. For example, you can do a select A, B from union, select C, D, and the first subquery has A and B, the second subquery has C and D, and it's still working, right? Why? Well, because SQL says that it is fixed arity arrays. So there is some such dark corners of SQL, but it's really just very few dark corners that create an issue there. Rather, the more interesting thing that SQL++ and Couchbase Analytics, the more interesting and more common, way more common thing that SQL++ and Couchbase Analytics tackled is the following. And actually, that's a question that you guys should have asked me while attending this. So I said, when you see a clause from collection as V, the meaning is that the V is ranging over the collection, right? And I told you, yeah, it's ranging over the collection, and first it's going to bind to the first element of the collection, and then to the second element, and so on. So the legitimate question there is, since we talk that this data have no schema, you would be justified to raise your hand and say, and what if this was not a collection, after all? What if the collection that appears there was just a scalar? What if it was a tuple? What do you want to see happening there, right? And what would you want to see happening if you say select x.foo as bar, and you have the variable x, and all of this is nice, and SQL compatible if x turns out to be a JSON object, which is equivalent to a tuple. But what if x was just a scalar? Right? What do you want to see happening there? What do you want to see happening when x.foo equals x.bar, and their types are incompatible, right? So this is the challenges that semi-structured query languages take positions on. And the positions that they want to take is that they want to tell you, hey, it's not necessary to define a schema in advance and to basically limit your data to the few options that this schema is giving you in order to have a working query. Rather, you can actually define particular semantics on what these things mean. For example, we have defined that the x.foo, when the x is not a tuple, is leading to a missing. Missing means I didn't find anything there. And if you basically go to a select clause and say, well, I didn't find anything there, and I want to say as bar, well, it will tell you, OK, then you have nothing. This, you're going to skip it. It's not going to be in the output either, right? So semi-structured data, an X that probably didn't have a foo, semi-structured outputs, some tuple that is not going to have a bar. Okay. And this works pretty well, because it basically says that you can do your analytics despite the fact that you may not have a schema for the data. And similar choices you can follow in the from clause and in the x.foo equals x.bar that are of different types. You don't have to basically crash things all the time. I have run a little faster because I somehow had in my mind that we're finishing at 3:50. So I'm heading towards finishing at 3:50, but that's OK. It will leave more time for questions. Let's skip, actually. That could be quite complex. If you'd like to, a bit of a follow-up here, there is some works that we had done at UCSD, which had gone into overviewing a lot of semi-structured query languages out there and saying, hey, what do these languages after all do, right? And NewSQL was one of the surveyed, prominently surveyed languages, since it was one of the most developed semi-structured query languages. So what we have done on these papers is that we went out, we looked at MongoDB, BigQuery, Jackal, NewSQL, of course, and a few others, and of course SQL itself. And we basically categorized their abilities. That is, categorized what do these languages do. After all, if you take the funny differences in the syntax away. Okay. And the way we did this is that we basically said, look, in some way, all of them do a subset of what we described here as SQL++, with the differences really being on the options that we described. What are they doing on these options? What do they do when, for example, you attempt to range over something that is not a collection, and so on. Okay. And these differences, we capture them formally in a very compact way that if you want to basically investigate, it's a good reading. Probably you don't want to investigate now because as this survey of capabilities goes, Couchbase Analytics actually covers all of these capabilities, so you can just as well use Couchbase Analytics and without looking too far for who has what. But if you use some other system and you want to compare whether you would like to go to SQL++, that would be a good survey to look at. I think let's open it for questions. Yeah. We had a few more features that we skipped over because I thought that it's 10 minutes less than it was, but that's OK.
You mentioned that these slides would be available somewhere. Can you tell us where to find them?
I don't know. I just gave a stick to the gentleman back there. Yeah. By the way, a longer version of these slides, which was much more on the part that here has been reduced to look at these papers, on the comparison part, and also with some part about comparisons to discussion of algebras related to the internal implementation of prior semi-structured query languages was presented at SIGMOD 2016. That was a 90-minute talk. So there, that part has, this slide has slides for it. Yeah. Yeah, you can also find it online.
So NoSQL and Couchbase Analytics is kind of subset of SQL++, right?
Couchbase Analytics is SQL++.
Oh,
It is, yeah.
implementation of SQL++, right?
It is, yeah.
And do you know anybody else?
And Couchbase Analytics guys may correct me, but they say, yeah.
Somebody
it
else
is.
on top of your head might implement the spec or
Someone might.
but not anymore, right?
I cannot comment. Yes.
What about, instead of iterating over, ranging over a collection in a from clause, can you range over a tuple as well?
Yes, actually, great. Now you help me go back to the slides that I skipped. Also, I would like someone to ask me about outer joins next. Okay, so there is two abilities. By the way, I believe these two abilities have not been released yet on Couchbase Analytics, but something like them will be, or them will be released very soon. So an ability to pivot from attribute value pairs to tuples, and then the ability, sorry, to unpivot from attribute value pairs to tuples, and then the ability to pivot from tuples to attribute value pairs. Let's go to them one by one. So notice here that I must forget the funny symbols. That's because it's like from the fully formal version. Imagine that I have a source, and the source is just one tuple, and it's named reading. Okay, and the reading has nitrogen oxide, 0.7, carbon oxide, an array 0.5 to 2, which probably means it was from 0.5 to 2. Okay, and imagine now that what I want to do is I want to get the output that you see down here. That is, the output is a collection. Remember, this means collection. If you get confused by it, just think of it as an array. That the order doesn't matter. And notice the output has unpivoted. That basically says gas, nitrogen oxide, value 0.7, right? So it took this and made them a tuple. Then it took the second pair and made it another tuple, right? How did this happen? Well, basically, here is a special feature on the reading, on the from clause. Notice the structure here. The structure says, I got two variables here, ranging the attribute name and the attribute value variable, ranging over the attribute value pairs I'm going to find here, right? So the G and the V first are going to click here, right? And you're going to get this binding. G is nitrogen oxide, V is 0.7. Then they're going to click here, and you're going to get carbon oxide array. And then there is an extra feature here that we didn't discuss before, which is this is the select row of nickel. It appears, I believe, now with many names in Couchbase Analytics, right? As select element, select value, whatever, whichever one you like. They all mean the same. Which basically this feature here says that, well, just construct exactly what you see in here. Right, exactly what you see in here. So here it says just construct a tuple with gas G and val V. This was not, I could just as well say here select G as gas, V as val. It would be the same thing. So that's not the important thing. The important thing is the from clause that managed to pivot the attribute value pairs into tuples. And the vice versa feature would be the one that would say that now I want to take tuples and, take multiple tuples and that have pairs of values, right? And take the one part of the pair, make it an attribute name, make the other one an attribute value. So let's plug together these two in a single example. I have, imagine a collection, readings. And it has got a tuple nitrogen oxide, all of that stuff here. And imagine that the query that you want to do is you want to say, I want to output for every tuple I have in the input, I'm going to output a tuple in the output that has only carbon oxide stuff. It could be carbon oxide, it could be carbon dioxide. I don't know, perhaps there's other carbon oxides. I forgot my chemistry. Let's assume they are. Carbon trioxide and so on. Here is how it does the job, right? So it says here the R is ranging over the tuples. So far, so good. Then comes the nested query. It says for every tuple, output. What should I output? Well, it says you should output the result of this query. This is the query that now it's going to pivot. Look how it's going to pivot. It first says it's going to unpivot and then pivot back again. Then first it says for each tuple have the G and the V range over the attribute name, attribute value pairs. Then keep only the pairs where the G looked like carbon oxide something. And that's now comes the special part. This select attribute is basically saying, hey, don't build here a collection, build a tuple. How you're going to build the tuple? For every G and V that qualified from the where clause, build another attribute name, attribute value pair. And done. And you see here, you have managed not only you managed to unpivot, do whatever analytics you wanted with it, right? Filtering, you could do whatever you want, joins, aggregations if you wish, right? And then back pivot if you wish. And of course, you could have examples where you directly pivot the input without having to go into an unpivot pivot example. Yes?
In JSON, inside tuples, the names of the attributes are strings, and strings are typically quoted.
Yeah.
But I noticed on your slides they're not. Is there a reason for that?
Yeah, so basically the reason to that, that was simplicity. But the little trick there is the different kinds of quotes. That is, there is the JSON uses double quotes for everything. SQL is using single quotes for the values and double quotes for the attributes. So, and Mike is adding and back quotes for the identifiers to make it more interesting. So there's a little bit to be done there on the, I think, by SQL compatibility. But Couchbase Analytics, I believe, takes the approach that is close to the JSON pattern, looks like a JSON pattern matching, which is very elegant if you deal with JSON.
Can I quote you on that?
Yes, please quote me on that. Yeah. So, but you should. But I agree with Don that if yes, on the Couchbase Analytics, there will be many more quotes in all the queries that you see here. Actually, not on this one. Actually, on this one, there wouldn't be. Because here it's all variables, really. And this has, oh, yeah, of course, but there would be on the result, yes. Okay, on the result, I was not putting them just for the sake of, it's an abstract model after a while. So I think the more interesting thing is what quotes we put on the query language. And I think some slides were raising an issue in the absence of a quote of what exactly is this thing. Okay, nobody wants to ask me about the outer join, so I think we're done.
Yes, what about the outer join?
Oh, great question. Fantastic question. Oh, our time is up, so I will have to to finish this offline. Okay, thank you, folks. That was